Let's take a look at some examples to illustrate having an inverse or not having an inverse. So suppose we have the following table. The table is going to determine a function that has an inverse. So I have t, and t is going to have the values 0, 1, 2, 3, and q, which is going to have the values of 4, 5, 6, 7. And so initially, let's look at it as q is a function of t. And remember, t is the input. And so as I look at my t values, I notice we use each one of them only once, and so it is in fact a function. Then I want to think of the inverse, and so what if I did the inverse? I would be thinking of t is equal to the inverse of q. And so now these are my inputs, and so if I look at the q's, 4, 5, 6, 7, they're used only once, and so that does in fact give us a function. Notice if I actually plot the points and connect them. So if I plot the 0, 1, 2, 3, and I plot the 4, 5, 6, 7, notice I have one line connecting each of them. So 0 is going to 4, 1 is going to 5, 2 is going to 6, 3 is going to 7, and if I look backwards, the same thing holds true. So we notice each t is mapped to one q, and each q is mapped to one t, so therefore the function's 1 to 1. Does have an inverse. Take a look at a second example. My t's are still going to be 0, 1, 2, 3, but this time my q's are 4, 5, 6, 5. And so now if I write down the t's and I write down the q's, now remember, please don't write down 5 twice, only write it down once, even though it appears twice. And now I do the mapping, you'll notice out of each of the t's I only have one item. That's a good thing. That's actually telling us that q is in fact a function of t, because we're using each of the inputs only once. However, when we look at the outputs, the 5 is used more than once, and so we can't say the opposite thing. We cannot talk about t giving us some sort of a function of q. And so because of that, this function is not 1 to 1, and so therefore it doesn't have an inverse, which we sometimes refer to as then not being invertible. So it's not invertible.